good to see so many of you in the morning here. So I'm not completely up, so maybe this gets me up too. So today we'll look at the problem of visual place recognition, and I'll try to do it in kind of a tutorial style. So we'll do some coding, we'll do some theory and so on. So before I get started, maybe we'll do a small quiz. It's not to test any knowledge, but just your vision, I guess. So are these two images the same place according to you? Yes, they are same. It's just different lighting conditions. One is in the summer and another one in winter. This was in Germany a few years ago. How about these two images? Are they the same or not? So actually they're not the same. So if you look closely, maybe if you look at some of the trees here and so on, it's not there in the other image, right? So they look very similar, but they're actually not the same. So broadly, if you just give it a glance, you could be wrong. How about these two images? They are the same actually. So it's not super clear, right? So once the lighting changes, once the environment slightly changes, you start to get confused. How about these two? Yeah, they're different buildings, so the tops have slightly different styles and so on, right? So yeah, so this question of figuring out if you have been at a particular place before is called as place recognition. And this has many applications. The reason we were studying it because robots tend to operate in the same areas over a long period of time. And if they come back to the same place, they need to recognize that I have been here before. That information is very useful because then you can correct your errors. Let's say you were thinking you were at some XY place. Now you have the ability to say, oh no, I've seen this image before. When I visited it last time, my coordinate was so and so. Now it's not the same. So you could use this information as an external input to improve your robotic navigation systems. So that's the reason why roboticists are interested in place recognition systems. But also in general, this is a widely studied problem in the computer vision community because you get, let's say, pictures of monuments or pictures of different areas taken by different people using their cell phones on different lighting conditions, different weathers, different days, and so on, right? And you want to collate them. So you want to find images that correspond to the same place in the world. That again requires techniques that will say these two images are actually the same place. Okay? So to do this, we'll build on a few tools. First, I'll introduce you to the concept of visual features. I know some of you are doing projects on image processing and so on, so you might be familiar with visual features. And within the features, there are typically two things you want to do. One is find key points. Key points are, in this example, like the dots that are given there. Those are points of interest. So those are points which you can re-identify if you see the same image again. So once you have those key points, the next thing you want to do is to have a descriptor. So how does that key point look like in a local area around it? And that's called as a feature descriptor. So we'll look at a few popular feature detectors, which will give you locations of interest points, and descriptors, which are a way to encode the local information around it. And once we have those two building blocks, we'll actually look at a technique for doing place recognition through what is called as a bag of words approach. So you'll learn about all of this going on. So these are the three parts, so to say, in today's tutorial. So let's get started with the visual features part. There are many features. It's a whole zoo of features that are available there. We'll cover four popular ones. These are Harris, Sheetamasi, Forstner, and a difference of Gaussian images. So I've picked these because they have some commonalities between them. So essentially, we'll be studying two families and see how that works. So the motivation to actually compute visual features is because the image itself is very complex. So image that you take with your mobile phone these days would be something like 4 megabytes big. So this is several thousands of pixels. If you have to process multiple of these images, it makes sense to have a representation that's more compact. The goal of visual feature detection is to find those points in the image that can provide you unique information about something in that local area. So one of the reasons you might want to do this is, for example, to match two images. Now I give you two images and you want to find out what pixels in image 1 match with what pixels in image 2. So in this case, this is Notre Dame, and these two pictures was taken at different time, right? So there's in one of the pictures on your right or on your left, sorry, you see the Christmas tree, and the other one there isn't one. But that's fine because there are several other key points that you can just identify, and then you could say, key point X matches with key point Y on the other image. So the reasons to do this are, one, just matching two images, knowing what pixels correspond to what other pixels. Two, if you want to create a 3D model of the environment. So if you know 2 points in the image space which correspond to each other, you can triangulate this to create a 3D model. You need a few points, about 4 or 5 of them to do this. But if you have a few matches, you can go from 2D to 3D. So you can do 3D reconstructions. If you take your mobile phone and take a few pictures of an object from multiple angles, you can then create a 3D reconstruction of this model or of that scene. And to do that, the first thing you need is corresponding pixels on image 1 with the same structure on image 2. So what are visual features and descriptors? So key points, or what I call as feature, but technically you would divide a feature into key points and descriptors. A key point is essentially a unique place on the image. It's unique for the computer. It may not be really unique for us seeing through our eyes, but for a computer, if it looks at that point, it should uniquely identify it as something that's distinct from its surroundings. And then we have the feature descriptor, which essentially summarizes what's the distribution of the pixels around that key point that you have. So it looks something like this. So for example, if you have the key point there at the top, so that's the key point itself. That's some XY location on your image plane. And then the descriptor will look like some vector. And so we will find out ways of computing that vector. But these numbers here, typically this is something like 128 numbers or 256 numbers. These numbers are a summary of how the image looks around that point. So that's the descriptor for that region in the image. There are various ways of coming up with that descriptor which have different properties. That's something we'll look later half. But essentially it will be a vector which then the computer can use to match two features, right? So essentially what you want in this image, for example, if you want to see if this local point is the same as this local point, you would compare the descriptors. If the distance between those descriptors is small, then you are sure that this is the similar area. Right? That's the idea. So in kind of today's content, we'll look at these four features: Harris corners, Shi-Tomasi corners, Forstner operators, and difference of Gaussians. And later on, we'll look at some descriptors. So first the question is, why at all are we interested in corners? Right? So corners are interesting from an image processing point of view because you have an area where there's a sharp change in image content from multiple directions. So at least two directions. So if a corner like a rectangle like this, the image changes a lot both vertically and horizontally. Those are areas that you can detect reliably. Right? So these are often distinct points. So of course, the ones that we see on the edge, it's clear that they are the corners between the foreground and the background. But the computer itself sees much more. So for example, all these points on the window sills, The windowsill itself is a bit dark. The building behind it is light. So it sees as a corner. So these are distinct points that the computer can use to say, okay, I can reliably relocalize this point later on. So one I said is that these are distinct points locally. So if I just zoom in and give you an area of that image, you probably wouldn't be able to guess where in the big image it is. But if you just look locally, it's a distinct point. Then the other reason is corners are invariant to translation. So if you move the corner a bit, the two images won't match. So the corners will only match if, let's say, both the horizontal and the vertical axes align up. Then there also something that won't match when you rotate. So if you rotate one image, you're trying to match image A with image B, but it's slightly rotated, two corners won't match. So you would need to rotate it in order to match, right? So that's the information that you're looking for. And corners are also somewhat robust to illumination. So your whole image might be brighter or darker, but the difference between the brighter places and or the foreground and the background would still be maintained. So that's again one thing that's interesting, because in the images that we saw in the earlier quiz, a lot of you were confused because the image content itself was quite different. But if you look at the corners, those are a little bit more stable, right? The other part that often people look at are edges. So edges are also good. You can uniquely identify edges as well, because they also separate foreground from background, but they have limited localizability. So if you have an edge, you have one axis along which you can freely move, and you can't really say where along that edge you are, right? So for example, if this is the edge separating the table from the background, if I say it's an edge, I don't exactly know where along the table I am, along the edge. But if I say a corner, I can pinpoint that it's this corner, right? So that's the advantage of having a corner over an edge. Great. So given that we want to find corners, the question is, how do we find these corners? And the algorithm we could start off with is fairly basic. So what is the property of the corner? So if you have your image at any pixel u comma v, so here we parameterize the image space in let's say horizontal and vertical u and v coordinates. Essentially, we can compute this by computing a certain value of how much is the image changing in a local neighborhood. So we take a local neighborhood of w. So think of this as a window. You have a key point, you take a 5 cross 5 pixel window around that key point, and you do the following computations. You take the image intensity at that pixel and subtract it from the image intensities around that pixel. So this is u plus delta v and v plus delta v. In a small area around the pixel you are interested in, you check the intensity values, you compute the differences and add them up. So if the differences between that point and its neighboring point when you add up is high, that's an indication that it might be a corner, right? So this is called as the SSD score, or sum of square differences. So you do the squaring because maybe you have a lighter versus a darker, or darker versus a lighter section. So you don't want your errors to cancel off. You actually want to add them up, right? So you want to find differences between bright and dark spots equally as likely as dark and bright spots. So you'll do the squared error there, right? So after this, you could do a little bit of math manipulation. So I'm sure you're all familiar with the Taylor expansion. So you could rewrite this term here, the u plus d u plus comma v plus dv, as this particular formula here, where you're just taking the first order approximation using the Taylor series. So the nearby image intensity or image function is approximated as the image intensity at uv plus a Jacobian times the distance you're away from that pixel. So this Jacobian essentially is the derivative of the image intensities that are there. So they are gradients. These Jacobians are also called as gradients. So if you write this in the matrix formation, you will see you could write f of xy. So this is the sum of squared errors that sum of squared differences. We'll end up with this formula where you have the Jacobian times the delta vectors squared. You could rearrange this formula to come up with the formula below, where you are essentially squaring these matrices. So when you're squaring matrices, you'll get one vector on the left, one vector on the right. So you'll get du dv with the transpose on the left, du dv without the transpose on the right. And in the center, you have this squared matrix with the Jacobians in different directions. So along the diagonals, you have the Jacobian along the x direction, which is the gradient along the x direction. In the other diagonal, you have the gradients along the y direction, and you have the cross gradients in the cross diagonal elements. So there's a little bit of math manipulation to come up with a structure that we can use later on. So this particular central matrix that you have here is called as the structure matrix, because essentially that's the only part of the whole equation which is carrying the information about how the image is changing around your center point. So that's the gradients or the derivatives that you have there. Then the question comes, all the information about how an image is changing along a point is given in the structure matrix. Then how do you actually compute edges and corners from this structure matrix? And even before that, how do you even compute this M matrix, which is the structure matrix that you have here, right? So these are the Jacobians along the x direction, so the squared of the Jacobians summed over the patch that you were interested in. And the same along the other direction y and xy and yx. But all these values are essentially summed over the window that you're interested in computing the corners or edges for that matter. So the computation actually involves a classic tool in image processing, which is image convolution. So to compute the Jacobians along the x directions, essentially this is the change in image information along the x direction, right? So what you're looking for, are there edges, are there borders along the x direction? And the way you could do it is to do a convolution operation with an x-axis edge detector essentially. You could use a kernel such as the Char or the Sobel operator. Doesn't really matter exactly which one you use. You'll find some changes in intensities on the x direction. With this one, you will find along the y direction. And then you can also find the combined xy direction by using one convolution along x and one convolution along y. So this is classic image processing to find x and y gradients. So if you look at those kernels which compute these convolutions, the Char kernels look like the ones on the left. So if you look at those numbers, you would see essentially the outer number is just a normalization factor. So if you add up the magnitude of these numbers, it's 10 plus, so 3 plus 10 plus 3, that's 16 times 2 is 32. So you're just normalizing this. And what this is doing, this kernel, when it operates on the image, is it's subtracting things on the top with things on the bottom. So it'll look for horizontal edges. So if you apply this convolution on an image, it'll find differences if they exist in the horizontal direction. And similarly, this will find things in the vertical direction. There are different schemes. You could either use the Char scheme or the Sobel scheme. Each one has slightly different smoothing properties. But essentially, what it will give is a difference. Yes.
Could you explain more about the Char and Sobel operators, like what they
are? Yeah, sure. So these are image kernels. So essentially, what happens is, so for a moment, we'll maybe just take Sobel because it's just easier numbers. So what will happen is that this matrix will get multiplied with some part of your image, right? In the image, assume you have a border or a edge in the center of that image. What applying this values means is that you will subtract one of the pixel on the bottom left with one of the pixel on the top one. So if there was an edge, right? So if there was an edge along the center, let's say on the top the image intensity was, I don't know, 100. On the bottom it was 100. and then when you apply this, the difference becomes 0. And this way you could actually identify if there are border regions there or not. And similarly, these are for 2 directions. The numbers themselves are the importance that you are giving to these different areas that you have there. So essentially, you'll find horizontal or vertical vertical numbers that you have, vertical edges that you have there. Yeah, later on we'll also see in one of the examples, you'll see the visualization of these things. So essentially with the structure matrix, what are we interested in? We're interested in finding the dominant directions. So for example, in the patch, so imagine W, which is your window patch, is the square that you're looking at. Inside that square, you're looking for corners, you're looking for edges, or you're looking for uniform structures. So this is not a very easily re-identifiable place. Ideally, we want one of those 2 things. And so we want to either see there is a corner or there is a edge. And the structure matrix will contain this information. How will this information be visible through the structure matrix? It's essentially through the diagonals. So if you look at the diagonal values, if the diagonal values are very big, so this is actually on the eigenvalue. So you take the eigenvalues of the M matrix, and if the 2 eigenvalues are very big, then you know there are 2 major directions in which your data is changing, and that's an indication for there to be a corner. Similarly, if you have one of the eigenvalues to be quite big, or in this case also just the M matrix to be big. So M, if you remember, is just the sum of the gradients along the y direction, right? So if you just add up the sum of the gradients along the y direction, that will be a pretty big number. So even before going to eigenvalues, you could even just look at the sum of the gradients. And if both of them are quite high on the x and y axis, then it's likely a corner. If it's only very high on one of the axes, it's a edge. Of course, if this data was perpendicular, you will see the bigger number on the other diagonal of the edge. And finally, if you have a uniform area, so uniform structure, so something like maybe parts of the screen are uniform, right? There are no real edges here. So in that case, most of the gradients will be 0. Nothing is really changing in here. Most of the texture is the same. So most of the gradients will be 0 there. Right? Yeah, so if the edge is slanted, you won't see them exactly in the diagonal. That's where we would need so the question is, what would happen if the edges are slanted and not along x and y axes? In that cases, this won't be clearly visible along the diagonal axes. That's when you need to do a eigen decomposition. You will find the eigenvectors and eigenvalues. The eigenvectors will be the dominant directions, and the eigenvalues along those dominant directions will be high. So that's how you usually deal with the rotations that are there. So we'll see that the check that we'll have won't be directly on M, but on the eigenvectors and the eigenvalues of M that you have. So yeah, so the key idea here to take away is if you want to find corners, the eigenvectors and the eigenvalues rather of the structure matrix will have 2 large values, and this will also take care of the fact that your corners are not aligned in that case. So based on this broad idea of looking at the eigenvalues of the structure matrix, 3 different methods were proposed roughly in the same time. So in 87 by Forstner, 88 by Harris, and in 94 by Shi-Tomasi. So if you've used OpenCV and if you've done some image feature detectors, these are the common ones that you would have used there. So all of them essentially use the same structure matrix, but they have a different way to say if analyzing those structure matrix, if something is a corner or not. Broadly, they perform similarly, with the exception of the Forstner operator or the Forstner detector, where you could even get a sub-pixel value for the corner. So most other methods will give you a pixel UV for the corner. The Forstner operator can give you a fractional part of the pixel as well as as the corner. So it's a little bit more accurate, which comes at the cost of more computation, but it's a little bit more accurate. So first we'll look at the Harris detector, which is probably one of the most popular corner detectors that are there. So Harris came up with this formula of essentially a ranking for the corners. So you have a score R, which looks at the determinant of M and the trace of M. So determinant and traces can be written using their eigen values, right? So you must have studied this in a linear algebra course where the determinant is the product of your eigen values and the trace is the sum of your eigenvalues. So essentially, if you take the M and you compute its eigenvalues, you can compute this value R, and the condition that Harris came up with is if it's a flat region, it means both the eigenvalues would have been small, and therefore the R value itself would be quite close to zero. It's a flat region. If one of the eigenvalues is smaller than the other, it's an edge, and you will end up with an R value which is negative. Whereas if both the eigenvalues are quite big, then you'll have an R value which is quite high. And then there is a sensitivity matrix called as K. You can fix it something between 4 to 6%. This was what Harris recommended. If you plot this criteria in a graph, you will end up with something like this. So what this slide shows is exactly the same thing as what we saw in the previous slide, but just plotted graphically. So if your R value ends up in one of these regions. So on the x-axis, you have the lambda 1, the first eigenvalue. On the y-axis, you have lambda 2, the second eigenvalue. If both the eigenvalues are large, so you are in this nice region, it's a corner. So both lambda 1 and lambda 2 are big. If one of those values are big, you end up in this section here or this section here, where one of the eigenvalues is large, but the other one is small. Whereas if both of them are small, you'll end up in this section here, which is just a flat section essentially. You could basically come up with this a threshold value and use the eigenvalues to make the determination. There's a slight difference that Chebrolu proposed. All the calculations are exactly the same. He made the criteria using just the smallest eigenvalue. So instead of doing both the eigenvalues, Chebrolu came up with a formula which says just look at the smallest eigenvalue, which you could compute using this formula, and test it against some threshold. If the eigenvalue is greater than some threshold, then it's a corner. So this is in some sense a simplification of what we saw in the Harris detector. The Harris detector's graph looks a little bit like this. It's a complex shape, whereas the Chebrolu detector would look like this. So since you're only looking at one of the smaller eigenvalues, if it falls here, it's flat. If it falls here or here, it's edge. And if it falls here, it's a corner. So this is a much simpler test to do. And therefore, oftentimes when you're doing visual odometry, where you have to do this multiple times, you end up using the Chebrolu detector because it's just a little bit faster to calculate. So Chebrolu came up with some values that work for images in general, because this have to do with the eigenvalues that you are comfortable saying what is a true corner versus what is a false corner. In practice, this is fixed. You don't really change it. The way you would do it is you would set a performance criteria on the true positives and the false positives rate. So you'll take a few images. You'll change your threshold, and you will see what's the percentage of true positives and false positives you're getting. And you'll settle for one where you're happy with the true positive rate without having a very high false positive rate. So it's something that you do empirically. Yeah. So similarly, there's the Foster operator. We will not really go into the details, but it's kind of similar to the Harris corner detector. But instead of doing the criteria on M, Forstner looks at the inverse of M, which is the covariance matrix, and using some criteria on the inverse of M, where Forstner looks at a shift. So essentially, he looks at what's the minimum amount I can shift without changing this covariance matrix a lot, because that the smallest shift which will explain the covariance matrix will be the exact point where the corner will fall. So it's a little bit more complicated, but the reason people do this is if you really want a sub-pixel estimation, you could go for the Foster operator. There's one more step that you do after the corner eigenvalue test, which is called as non-maxima suppression. So non-maxima suppression is that you don't want many corners at the same point, because the test will pass, if you're at a corner point, the test will pass maybe for a point 1 pixel below the corner and 1 pixel right of the corner as well. All of these are essentially the same corner as far as we are concerned, right? So you don't want too many corners within a very localized area, and this is done by using a non-maxima suppression that you have. So if I ask you, I have these three patches where the corner has been detected. One, the corner has been detected here. In the second one, it has been detected here. In the third one, it has been detected here. Which one do you think is actually the best corner to detect? The first, the second, or the third? First, I heard a lot of first. So why is first a good corner to detect? So all of them have the corner inside. You have localized them. So why is the first one a good one to detect? So the difference is the first one has only a little bit of the, this is not really very visible, right? Okay, so maybe this question is not very helpful. So what is happening is in the first one, the corner is only captured in one end here. In the second one, there's more of the corner being captured. And in the third one, a lot of the corner has been captured. And actually, the third one is the best one because there isn't a lot of room to move in there. So you'll localize it much better than the other two ones that are there. Because I think this color is not a good one to use for the slides. So yeah, third one is the best one. So when you implement this, typically you need to do first RGB to grayscale conversion. So most of your images will be colored, but this technique is typically done on grayscale images. And the other thing you want to typically do is a little bit of smoothing, because most images have a little bit of salt and pepper noise or some other artifacts that are there. So oftentimes when you do image processing steps, it's good if you do some kind of a Gaussian smoothing. It'll decrease these noises, and then your detectors will be a little bit more robust to noise. So if you plot this as a chart, most of the corner detectors can be thought of as the following steps. So you start with the image. And then you compute the convolutions to compute the edges. So these two steps are the convolution. You will then get gradients in the x direction and gradients in the y direction, so the jx and the jy. Then you do the squares. If you remember, our formulas had squares in the structure matrix. You do this for jx squared, jy squared, and also jx, jy. And then you will end up with you'll just sum those up. So this is to sum up the values in that window. And then after that, in the Chebrolu, we'll look at the minimum lambda. If you're using the Harris corner, you look at the R values. But this part will change depending on the implementation. But the rest of the part is usually the same. All the computations are the same. It's just the last part, the condition that you use to say something is a corner or not, changes. Right? And then the final step is a non-maxima suppression. So you need to make sure that you don't have too many corners that are close to each other. So this is the, in a way, recipe to compute corners given an image. So in this, you'll end up finally with something like this. So if you have these areas where you have these squares which are rotated arbitrarily, you want to find the paths where you have the edges. So the different colors that you see here are the outputs of different detectors. I think one is a Harris detector, one is a Chebrolu, and another one is a Forstner one. And each one of them has a slight inclination towards being a little bit inside, a little bit outside. But for all practical purposes, they're kind of good enough. So yeah, so once you have this, then you have these detectors that you can compute on multiple images. And now you forget about the image itself. Now you could just think of the image as this collection of points where interesting information is. And you could use that information in order to do the matching, for example. So just a quick a quick summary. So in practice, all the three detectors perform similarly. So unless you're looking for something that's very precise, it doesn't really matter. So if you want a sub-pixel accuracy, you go for Forstner operator. Harris was, let's say, the earliest operator. So a lot of the initial work in computer vision you'll see uses Harris detectors. And then Shi-Tomasi is a little bit faster just because the test is a bit easier. And for example, if you use OpenCV and you do a corner detector, it's computing the Shi-Tomasi corner as the underlying corner detector that's there. Okay. So that's family one of, let's say, corner detectors. The other family which is very popular is what is called as difference of Gaussians. So the task is the same. We still want to find uniquely identifiable places in the images, but this does it in a very different way. So the difference of Gaussian way of computing key points actually does a little bit more than just finding corners. It finds corners, it also finds edges as well as blobs. So blobs are, let's say, one big structure that is consistent in the environment. So maybe a blob could be, if this is the whiteboard, and so all of this, let's say, is black. As a uniquely identifiable key point, describing this whole patch, or let's say getting the center of this patch, is also a uniquely identifiable or re-identifiable feature. So if you have sharp structures, of course the corners are good places to find, but also if you have uniform patches, but the whole patch is separate from its background, the patch itself can be considered as a larger blob key point. And the difference of Gaussian key points are able to capture these blob examples as well. Right? So how do you do the difference of Gaussians based key point detection? So this has 3 steps. Essentially, it's doing the difference at different scales. That's why it's also called scale space pyramid. So difference of Gaussians over scale space pyramid. When we see the image, it will be clear. So it has 3 steps. One is you smooth your images to different levels. So you take your original image, you apply a smoothing. So things become slightly blurred. So you apply X amount of smoothing. Next, you apply 2 times that smoothing, and third time you apply 3 times that smoothing. So you blur the image a little bit, you blur the image a little bit more, and you blur the image a lot. Once you do this is the step 1. The next step is you look at the difference between these blurred images. And we'll see that the difference between the blurred images will capture things like corners, edges, as well as blobs. And then you do some maxima suppression, which we'll see. So this is a little bit clear if you look at the illustration here. So what's happening at the bottom is you take your original image, which is the bottom layer here. Then you apply, in this case, 4 scales of blurring. So this is slightly blurred, this is more blurred, this is even more blurred, and this is maybe completely blurred. Then you take differences between that layer and one more blurred layer. So you take the difference between the original image and the first blurred layer, the first blurred layer and the second one, the second and the third one, and the third and the fourth one. So you now have difference of these Gaussian blurred images. And then in that difference, you find the points which stand out. So for example, in this case, you look at these different scales. So these are different scales of blurring. And you find out that this particular area stands out with respect to the other values that you have. So that's a corner point, for example, or that's a point of interest. And to make it more robust, this is also done at different image scales. So why is this done? So for example, if I take an image of this room from here, and I see that clock at a particular scale, I go closer maybe to you and take another image, that clock will appear bigger. So now you have features which have been seen at different scales. So how do you identify the same object in the environment that you have seen from different distances? The way to do that is to take your original image, I, and maybe reduce the resolution to half, reduce the resolution to 1/4, 1/8, and so on. This way, you'll capture the different scales that exist or that could come during your test image time. So how does this actually look when you run it on some example? So what you see on the right here, yeah, this also is not super clear, but what you see there is the original image, and here you see some black dots. Those black dots are the areas that are shining in the difference of Gaussian representation. So this is basically, you looked at the difference between the original image and the first blurred image, and you looked at areas that pop out, and those areas which pop out are these points that you see here. So those are points of interest that you have. So to look at the scale space representation more closely, you can look at these different blurred images. So when I say adding different Gaussian blurring, that's what's happening in the two rows. So on the top left is the original image. Then we have blurred it using a kernel of 1. Then we have blurred it using a kernel of 4, 16, 64, and 265. So as you can see, the more you blur the image, the features you're looking for are big. So for example, in the biggest blurred image, you see that there's a big object somewhere on the left hand side, right? So there is something that's big, like a tree here. That feature won't be really visible in the full resolution image because there you see many more details. So what the scale space representation does is that it gives you uniquely identifiable features at different levels of blurring, and that gives you the ability to actually detect different sizes of features as well, not just the same size that you have. So to summarize, essentially what you end up is these blurring filters are removing high frequency information. So when you want to find big chunks of uniquely identifiable things, you want to blur out the things that change at high frequency. And by looking at the difference of these blurred images, we only look at the frequencies which are essentially that lie between the two levels. So for those of you who are studying maybe communications or electronics, this is essentially a bandpass filter. So the difference of Gaussian is doing a bandpass filtering on your image to find interesting points which can be re-identified. Right. So when you so maybe when you look back at the slides, this will be better. So when you look at the difference of Gaussians on the right hand side, you will see the different scales at which this has been done. So yeah, so this is in general the overall recipe for the difference of Gaussian widths. You would have to follow this up again with the extrema suppression step, where you will check for blobs and corner structures. Both will have strong responses. You want to remove the edges. Edges are typically not very good for image matching, so you want to remove the edges, and you can do it using the same test that we had before. So we had the eigenvalue test that we used in the Harris detector. You could use a similar test to remove the edges, because the DOG filter will give you blobs, edges, and corners, and if you don't want edges, you need to remove them. So that's the operation that you do here. So just as a summary, we saw two kind of families of corner detectors that are there. One is using the ideas of the structure matrix, looking at the eigenvalues in a local area, and the other is looking at differences of blurred images. So this is a more frequency way of looking at the images. So you're trying to get rid of, or you're trying to capture those frequencies which indicate towards a change in the intensities. Right? So typically corners and blobs are considered good key points because these are stably identifiable. And most of these key points are dependent on image gradients. So in both of the cases, even though we were doing a difference of the blurred images, it was capturing some kind of image gradient inside there, right? And the goal is finally to find those points which are uniquely identifiable, right? So that's kind of, let's say, for this part, the theory bit. So I'll show a quick demo on Python notebook of what we studied essentially. So we'll share these notebooks later on, so you can also run them, change the parameters, and maybe also you can add some more tests or play with the settings. Okay, I guess it will take a bit of time to connect, but I can say in the meanwhile. Okay, it's connected. So this is the Python notebook for the Harris corner detector. So yeah, it's basically a from scratch implementation which you could also play with. The first part of it is just creating some synthetic test data. So I'm creating some corners of certain sizes, creating edges, and creating flat spaces, because those are the places where we want to test if our detector works. Then we compute gradients. So in this case, I've done a much simpler version of the gradient computation than what I showed in the slides. In the slides, we applied a Sobel operator or a Schar operator to do the gradient detection. But in principle, gradients are differences in intensities, right? So the simplest formula for that is take a pixel in your image, compute the difference of it couple of pixels away, and divide by the distance. Right? So in this case, I just took 2 instead of 1 because it just becomes slightly less noisy. So this way you will get a gradient estimate of each pixel in the image, but you can also apply your convolutional operators that are there. Then you have to compute the structure matrix. This is the M matrix that we studied about. So the structure matrix, you will have to sum up the gradient squares over the window W. In NumPy, this is fairly straightforward. So you take the gradients, you square it, you sum them up, you will get the elements. You put those elements together to get the structure matrix M. Once you have the structure matrix M, you need to apply the test. The test here is on the response value R, which we said is the determinant of M minus K times the trace of M squared. And if you do this using NumPy, again, it's very straightforward. So you can get the determinant, the trace, and then you apply this formula to get the response value. And then you have to choose a threshold. In this case, I chose 10 power minus 4. And then if the threshold is, if the R value is greater than the threshold, then it's a corner. Otherwise, it's an edge or it's flat. So this is the classification criteria that I used. And then you can run this whole bit. So let me just, okay, these are all run, I guess. So maybe I can do this. So we'll visualize the results for this particular element. So, okay, so these are the 3 patches that are generated. So on the left is a corner patch, then is an edge patch, and then is a flat patch. Ideally, we would want the Harris detector to only detect an edge on the left image, right? And if you look at the corresponding M matrices, you will see that the corner patch has large gradients in the diagonal elements, whereas the edge only has 1 large diagonal value, whereas the flat paths have almost 0, or in this case, since it's synthetic, exactly 0 gradients that are there. And when you apply the filter or you compute the R, you will see that the R value for the corner will be very high, for the edge will be some negative value, and the flat will almost be 0. So you can also do the analysis at the eigenvalue level. So you can look at the individual eigenvalues of the M matrix, and in the corner case, we have 2 very large eigenvalues, lambda 1 and lambda 2, whereas in the edge case, you only have 1 large eigenvalue and the other is close to 0, whereas the flat case, you have 2 small eigenvalues. So this is for a very toy example, how you can do a corner detection using a Harris detector. So if you want to make this into Shitomasi, you just have to do the tests on the smallest eigenvalue instead of doing the test on the R. So this is good, but in the end, we probably want to test it on a real world image. And in this case, we take this building image, which is one of the classic OpenCV examples that you get. And it's also a good test because there are lots of corners in there, and all the red points that you see here are the Harris detected corners that you have. So this is what you wanted, right? So you wanted uniquely identifiable corners. So for example, nothing was really found in this uniform region area because those don't really have any changing gradients. So the Harris detector can't find blobs, it can only find corners that you have. Right. We'll see these the DOG in a later example where it also finds other areas such as blobs. So any questions so far? Because we're at the key points part. Next, I'll start the descriptors. Or any questions on the code as well?
So like how are we getting the information about the pixels?
About the?
Pixels, like how are we getting the vectors of the pixels? Like how did you find the pixels?
So pixel in an image is just the intensity value of that image. So when you take an image, it has 3 channels. It has R, G, and B. Each of the pixel will have a value between 0 and 255. Let's say we convert it into a grayscale. 0 is black, 255 is white, and any value in between is some gray color that you have there. So that's the pixel value. So when I'm talking about intensities, it's the value of the pixel that's there in the grayscale image. Yeah.
So like how do we like analyze the image to get these values?
The pixel values or the corners?
The pixel values.
So there is no analysis there per se. So when you take a image, the converter, you take an image, inside your camera will be a sensor which will map light to some values, and these values will already be in one of those ranges that you have. So you don't have to compute that. That's what you get as input. Yeah. Any other questions? Okay, maybe a question from me is, how many of you have actually used the Harris or one of the other detectors that I talked about? Okay, a few of you have used it. So maybe you can tell us, what did you use it for?
Sir, I have a question actually.
Okay, go for the question.
Sir, after applying some filter kernels, why does the output image have black pixels at the edges?
So in the example here,
not in this. There's a good website called satosa.io,
okay,
which visualizes how kernels are multiplied with the image pixels.
So you're asking why the edge pixels are black when you apply a convolution operator. So when you apply a convolution operator, you're taking your matrix and multiplying with the pixel values that are there, right? So what happens for the cornermost? So if you have an image like this, so let's say this is your image with some pixel values, whatever, 7, 23, 155, 0, things like these are your pixel values. When you do a convolution, let's say we are doing a 3 cross 3 convolution. So if I'm doing a convolution about this pixel, a 3 cross 3 convolution around it will multiply values in this region. So you'll take the kernel values and multiply it with the image intensities that are there below. But what happens for a pixel that's at the border? If I consider the value here, the 3 cross 3 matrix for that would actually lie outside your image, right? So this matrix will lie outside the image. And oftentimes what you would consider is, for edge pixels, you will just consider the underlying image quantities as 0. So this one is of course 7. And therefore you end up with these sides which are black. One way to mitigate this is you can actually just copy the last column of your values. You can replicate it twice more. So this way you can kind of extend your image saying the last columns are the same as the inner columns, and then you do this. So it's just the artifact of the assumption that you're making that the outer pixels outside your image region is actually just 0. Yeah.
Thank you.
Okay, maybe I'll follow up on the original question then. So some of you raised your hands for saying that you use these image corner points or key points. Maybe if somebody can volunteer, what did you use it for? So who had raised their hands before? I'm sure some of you must have used it, especially if you're working with images in your projects. You would have used some kind of a corner detector.
So basically, I was working on Krishi Cobot team. So there we were requested to do shape detection using image processing.
Mhm.
So we get LiDAR data of 2D LiDAR which is already placed on the e-board. So we'll get a set of LiDAR points. I converted that into image. So using OpenCV pre-libraries, I was I was asked to detect the shapes. So for detecting shapes, we need to detect edges, right?
Yeah.
And we need to detect the corners as well to separate the line segments.
Yeah.
So that's where I used corner detection.
Yeah, that's a very common use case for kind of shape detection or object detection,
Yeah.
where you could use key points to get the boundary. But actually, in the Harris corner detector, we were getting rid of edges just by saying, okay, only one eigenvalue is high. But in your case, you actually want to keep the edges as well. So you could also modify this Harris corner detector to make into corner and edge detector if you accept both two high eigenvalues or one high eigenvalue.
Yeah, I was using some other algorithm for detecting lines.
Yeah.
So for detecting corners, just used Harris
Yeah.
once. Then I didn't use Harris. I just
So now you know what's inside the Harris detector, so you can actually go modify it to serve your purpose. So
Yeah.
for many years, I actually did not know what's inside a Harris detector. It's one of those tools you just use because you get corners and you move on with your life. But actually knowing how the internals of these detectors are implemented helps you, for example, in a custom case where you're looking for something specific, right? Okay, thanks.
Yes, sir.
Any other questions? So then I'll start with the visual feature descriptors. So till now what we saw is how to get those points. But the next question is, how do you describe the local area around those points? Right? And we'll look at a few things. We'll look at, broadly we'll look at SIFT, which is one of the most popular feature descriptor, and then brief and ORB. So SIFT stands for scale invariant feature transform, and brief are binary, brief and ORBs are binary descriptors which are very fast to compute. So we'll see this. So again, the motivation is the same. You have these unique key points, but when you zoom into, let's say, one of these key points, they might look very similar locally. For example, if I take this key point versus this key point, and if I zoom into a patch there, they both will look very similar, right? So you need ways to actually describe what the areas around it look like. And you can do this using a feature detector. So previously we saw key point, which is a locally distinct location. Now we'll see how to come up with the descriptor for that key point, which summarizes the structure. So we had this before also. We said that we'll create this vector. So for now we know how to locate them. So key point is done. Now we want to know how to come up with the array which describes that area around the image. And we'll see these three features. So the SIFT feature, which is the scale invariant feature transform, which was, I think, invented in 1988, and it's still probably one of the best feature descriptors that is there. So it stood its test of time. And the other two descriptors are what are very commonly used in robotics projects, which is brief and ORB. The reason is brief and ORB are about 100 times faster to compute than SIFT, and we'll see why. And it's quite surprising why they even work. So these will be the three descriptors that we'll look at today. So the reason you need a descriptor for the most basic use case is of image matching, right? So let's say we compute the features and compute its descriptors. And the way you would do feature matching is like the following. You would look at the descriptor for this key point, and then you look at each of the key points and compare it against each of those descriptors. And you say the descriptor which best matches the other descriptor will be my match. So you'll take one key point here. It'll have some descriptor, let's say a 128-bit descriptor. On this other image, let's say you have 100 other key points. You will match or you will compare this descriptor with 100 other descriptors and say descriptor number, whatever, 37 has the best match with my current descriptor. That's the reason you want the descriptor to even exist. And once you find a few of those, you can then do other image processing tasks like 3D reconstruction and so on. Okay, so our aim will be to get the F, which is the descriptor in this case, the vector F. And if you look into the literature, there's a whole kind of zoo of these descriptors. So there are descriptors which look at gradients, called as the histogram of oriented gradients. Then there is SIFT, which we'll look at today. And there's SURF, which is a speeded version of SIFT. Other things like globe, and there are some other binary feature descriptors. So let's say in the 90s, if you were a computer vision researcher, your aim would have been to come up with a new one of these because you wanted some extra properties and so on. So we'll look primarily at these four today: SIFT, brief, ORB, or these three, and look how they differ from each other. So with this SIFT descriptor, the design rules were something like this. So Lowe, who invented this descriptor, wanted the following properties. The first property was the descriptor should be invariant to image translation. So if I compute the same descriptor, I take an image and I move a little bit and I take the image again. So the location of that point will change in your image, but the descriptor should still remain same. That means image invariance. So he wanted invariance to image translation and image rotation as well. So sometimes your camera, let's say, is horizontal, but maybe sometimes it's rotated. This is particularly the case if you work with UAVs or quadcopters, which move in the full 6 degrees of freedom that you can have. So you can observe the same interest point from different viewpoints, different angles. That means your image descriptor should also be rotation invariant. Then the third thing he wanted is a scale invariance. So if I look at an object from distance x and I look at an object from half that distance, the descriptor of that region should be still the same. So I should be able to re-identify the same object whether I see it from 10 meters away or 5 meters away. So how can I come up with a descriptor? So these were the design kind of specifications, so to say, for the descriptor that Lowe worked with. In addition, the SIFT descriptors also tends to be partially invariant to illumination changes. This is because it uses a difference of Gaussian key point detector, which itself is partially invariant to illumination changes, and there is some affine and 3D projection properties also that's there. So as a result of these properties, the SIFT detector became, in a way, the de facto gold standard for doing image matching from different angles and different distances, particularly if you have some illumination difference as well. So very robust way of describing an image patch. So if you look at a SIFT feature, it will have 4 components. So the first component is P, which is the pixel location. This is what the detector would give you, something like a Harris detector can give you. SIFT uses the difference of Gaussian detector as the default setting, but in principle you can use whatever detector you want. So P is the pixel location. S is the scale in the DOG. So we applied various amount of Gaussian noises, right? So at which scale of Gaussian noise did I detect that feature? So S is that. This is again coming from the detector. R is the orientation of the local gradients. So this is something you need to compute. So you look at a patch, you look at the image gradients, and you find the dominant direction that gives you the dominant orientation. This is needed because if you have the orientation of a patch, then if you see the patch vertically or if you see the patch at an angle, you can then say, if I rotate it by the orientation angle, they should match. So by adding this additional information about the orientation of the patch, you can become rotation invariant, which was one of the specifications that they had. And finally, you have the descriptor itself, which is a 128 dimensional vector, which is generated from local image gradients. So these are the 4 things that you need. And if you look more closely, you have 3 things which are location dependent or viewpoint dependent. Your position of that feature, your scale, and the orientation will depend on where you took the image from. If I took the image closer to the object or farther away from the object, or if I took the image rotated, or if I took it horizontal. So those 3 things are viewpoint dependent, whereas F itself will be viewpoint independent. No matter how you take it, F will be the same. And that's a very powerful property, because if the F vector will be the same no matter how you looked at it, you can match it no matter how you took the image. So that's the idea of having this invariant feature that's invariant to these different properties. So how does the SIFT computation work? So you take your input image, convert it into grayscale, and then compute some key points. So these key points are the yellow circles that you see here. And yeah, maybe it's not super clear, but these key points are also showing some line. So it's like a clock with a line that that's pointing towards the main orientation of that patch of that key point. So the key points themselves have an orientation towards a nominal direction, so to say. And then the descriptors will be these square patches around that key point, which will summarize essentially the image gradient information that's there. So we take this key point, for example, XY position. We have a patch. The size of the patch is actually a property of the scale at which that feature was detected. If this feature was detected to be big, you need a bigger patch to capture that feature. So what happened here is that the feature vector that was detected here, the feature underlying was quite big. So you needed a big patch to describe that feature. Whereas maybe one of these features was very small. It was detected at a lower scale. And therefore, to summarize it, you only need to look at a smaller area around it. So in this case, the image is being explained both using small points, which are these small squares, but also big points, which are these big squares. So unlike Harris corner detectors, which will only look at corners of a particular size, this can look at features at multiple scales that you have. So if you look at it far away, or if you look at it from a closer point, you have some things to identify that are there. So the next question comes, what calculation can I do within this patch that gives me this 128 dimensional vector that is unique about that patch? So to do that, the formula is kind of given. You take a 16 cross 16 pixel area around the image point at that particular scale. So by doing it at that particular scale, you also cover bigger areas than the original 16 cross 16 image. Then you create an array of orientation histograms. So you compute the gradients. Gradients are the orientations. And then you create a histogram of that. So histogram is nothing but a count of the angles. So what's done in the SIFT descriptor is that you break up your bins into 8 orientations. So something like 0 degrees, 45 degrees, 90 degrees, 135, 180, 235, and so on. So you break your 360 degrees into 8 chunks. And then depending on which is the closest value that your array is falling into, so your gradient here, for example, is falling into, you increase the count of that particular bin. So you are, in a way, digitizing, or rather a correct way would be say you are approximating it to the nearest bin that you have. So it's a much more coarser representation. And once you do this, you can then you do this for 8 orientations and 4 cross 4 histograms. This ends up being 128 values. So if you look at a particular example, let's say if you have a feature that's being detected with this orientation on the top left, you take the 16 cross 16 pixels that are in that image. So this is the original image that you have. You of course compute the grayscale image and you compute the gradients that are there. So you break this 16 cross 16 image into 4 cross 4 patches. So you have 16 blocks now. For each block, you will have a 4 cross 4 sub block that's inside there. So you'll have 16 gradients, 16 values of orientations that you have in there. So those 16 values will form one histogram. So you can pick up one of those blocks, and that will tell you maybe three of the orientations were 0 degree, 4 of them were 45 degrees, and so on and so forth. So you have a 8-bin histogram per block. So this is 8 values, plus you had 16 of those. So you can just concatenate them. So you can put them next to each other. This way you have 16 times 8, which is 128 values, right? So this is the F vector. This is the descriptor of that local region. So one question you might have is that this is just counts, right? So counts are integer values. So why is this SIFT actually a float vector? So if you have ever computed a SIFT feature vector, it will be a float values of 128 bits. The reason is you just don't do counts, you do something more. So for example, if I have a orientation of let's say 42 degrees, I can treat it as mostly 45, but a very, very little 0 degrees. So you can take a linear interpolation between the bins that you have. That gives you a decimal value in terms of the counts. Plus what's also often done is, it's the gradients which are to the center of that block get more weightage than the gradients which are to the outer of that block. So there is a preference given to the center of this. And so on and so forth. And because of this, you end up with some float values that you have. But in the end, it's just a 128 bit float value that you have. So the algorithm itself, the actual recipe itself, was actually not known for a long time. Only about 5 years ago, I think the patent for the SIFT feature was expired, and we learned what the actual recipe was. So there was a paper, of course, about SIFT which had general rules, but the actual implementation was never really known. And so SIFT was only available as a binary that you could put into your code, and you actually did not know what happened inside that binary. So finally the patent has lapsed, and so now you can really look at what's happened. And therefore many people try to recreate SIFT, but every SIFT was different because there are so many hyperparameters that you could change. In the end, it's just up to you how you want to mix those values to come up with a 128-bit vector. So this is the 128-bit vector, which will now describe the image. So at a high level, you have your images where you have detected your key points at different scales. That's why you see different circle sizes that are here. For each of those key points in the region around it, you compute the image gradients. Given that image gradients, you compute the image histogram, and then you stack them together to get your feature vector. So that's overall your SIFT approach. So you compute the key point via difference of Gaussians, compute the descriptor essentially using the local orientations. So the only thing that has gone into your histogram is the local orientations and some way of mixing them to come up with a value. And when you have this, you can apply them to your matching problem. And what you will see is that the descriptor, for example, of this top bit here will match with the descriptor of the top bit on the other side, because the local area is quite unique, right? So there's one small problem that occurs with this is the green lines that you see in this case are actually correct matches, but the red lines that you see are actually incorrect matches. And if you zoom into it, you will see why. So this structure that you see on this part of the church here is actually very repetitive. So if you zoom into very local areas of that image, these are some kind of statues that are there. At this image resolution, it's very difficult to distinguish between one of these statues with another statue that's right next to it. So when you have visually repeating structures, their local descriptors will look very similar. And that's the reason why one of these key points got matched to another statue, which looks very similar as far as the descriptor is concerned. So even with a very good descriptor, you should always assume some of the matches will be wrong. And so you will need in your larger algorithm a way to make sure that you are removing these wrong matches, right? Is anybody aware of a method you can use to throw away those bad matches in red and just keep the green ones? Yeah, so maybe you can tell it in the mic, maybe, yeah. Okay, so ransack algorithm is one such one. Does anybody know why ransack works, or what happens in a ransack algorithm that allows you to throw away those three? Yeah.
To fit the best fitting model, and then it classifies them as inliers and outliers.
Yeah, so broadly that's correct. So in this case, the model will be the image transformation between those two two images. For example, the model is how do I warp image 1 into image 2? All the green bits will warp them in one way, whereas the red bits will warp them in different way. So you take a subset, let's say 3 or 4 of them randomly, and then you check against the other match that you get. Let's say one of these wrong matches. The wrong match will not agree with the answer that the rest of the group will say. So this is the randomized consensus algorithm. So that's one way to deal with this. So very good. So ransack is, let's say, the de facto way to do outlier rejection. Right? Very good. So before ransack, there's a couple of steps you could still do, and this is what David Lower, the original author of the descriptor, did, and he did this using 3 steps. So when you're matching a feature P with a feature Q, you take a query feature Q and you want to find the closest feature on the other image. Let's say you're confused between 2 other features, P1 and P2. So the first check is just the Euclidean distance. Compute the distance of your query feature Q to your 2 other features P1 and P2. That gives you the distance between those 2 features. Check if that distance is less than a value. So if the distance is more than a value, then it means those 2 descriptors are not very similar. But the next test is actually quite interesting. The third test says only accept those features as matches where the best match, which is the distance between Q and P1, is at least twice as good as the next best match between Q and P2. So you compute 2 distances between the descriptor in your query descriptor and your best match in the other image. You compute it for top 2 matches, and then you see, is the best match at least twice as good as the second best match? And the reason to do this is to remove ambiguities. So if 2 scores are very similar, it probably means that there are 2 regions which also look very similar. So to be really sure, you only say, I will only pick those matches as true positives, which are at least twice as good as the next best estimate that we have. By doing this, you do throw away some of the good matches that you might have, but often for most image processing tasks, you only need a few good matches. It's better to have a few good matches than many matches with a greater outlier ratio. So that's the reason you do this step, a lowest ratio step. But even after you do a lowest ratio step, you might end up with some bad matches, and then you have to do things like ransack to deal with it. So it's kind of a cascading sequence of things that you would need to do. So I kind of covered that. So lowest ratio will work well in most of the cases, but there will be still a few outliers, and you remove that using ransack, or there are also some other methods to remove the bits. So maybe at that point we can take a short break, and then when we come back, we'll look at the binary versions of the descriptors, and finally the originally promised task of retrieving the images that look similar, like the place recognition task. So finally we'll put together these to solve the place recognition tasks. Right? Okay. So now we saw the SIF descriptor. It's very descriptive in the sense that SIF descriptors are known to be like you will get very reliably the matches even when the images change a lot, but they're fairly complex to compute. So you have a lot of gradients that you need to go through, compute the histogram. It's a fairly time-consuming task. We'll see later on in one of the examples that it's roughly for a good-sized image, a HD image, it's about 1 second per image. So to compute the SIF descriptors per image is about 1 second. You might say 1 second is not much. So if your task is offline analysis, that's okay. But when you're doing robotics, you typically need to work at something like 20 to 30 times a second. So that's not fast enough to take decisions when you're doing making decisions in real time, so to say. So that's the reason simplified versions were invented, and some of the most simplest ones are called binary descriptors. So the idea of a binary descriptor is you're given an image patch and you need to come out with a string of ones and zeros which will be unique to that patch. Essentially, you're coming up with a signature for that patch, which is just a combination of ones and zeros that you have. So the recipe for a binary descriptor is straightforward. You take a key point. You can take a key point coming from a Harris detector or a Shitomasi detector or anywhere else. Select a patch around that key point and then select pairs of pixels. For now, just arbitrarily pick 2 pixel locations. So if you have, okay, actually I have this in the next slide. So if you have this image here, which is a patch, you pick certain pairs. So in this case, let's say we pick the pair 5, 1, 5, 9, 4, 6, 8, 2, and 3, 7, where these locations are the indices. So if you have a 3 cross 3 matrix, the index for these are given here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. You have this image patch. Now pick 2 pairs. So here I say pick 5 and 1. So 5 is this guy and 1 is this guy. And then do the following test. Check if the intensity at the first sample location is less than the second sample location, then the output is 1. Otherwise, the output is 0. So if we apply it to this example, the intensity at 5 is gray and the intensity at 1 is black. And typically in image processing convention, darker numbers, darker areas are closer to 0 and brighter areas are closer to 255, for example. So this is a bigger number minus a smaller number. So that's positive. So positive meaning I have failed this test. So I of S1 is not less than I of S2. It's actually greater than I of S2. So the output is 0. So the output of this is 0. So this is the first element of my string. Next, I do between 5 and 9. Will the output be 0 or 1? 5 is this one and 9 is this one. So maybe it's not super clear. 5 is a little bit lighter than 9. Will it be 0 or 1? It will be 0 again because lighter minus darker one is positive, again 0. What about 4 versus 6? 4 is this, 6 is this. Yes, because it will be again, it will again be 0 because lighter is a positive value greater than this. So again, the test failed. 8 and 2, okay, I already showed. 8 is dark, 2 is white. So 0 minus 1 is negative 1 or 0 minus 255 is negative 255. So your test that I of S1 is less than I of S2 passed. So that's 1. And final one was 3 and 7. So 3 is this and 7 is this. Again, it's a darker versus a lighter one. So again, 1. So now the signature for this patch is 00011. So the way the computer encodes that part of the image is just through this string 00011. If this were a CIF descriptor, it would have been first of all much more longer, and also you would have to compute gradients and all those other calculations that we did. Now what are we doing? We are just doing comparisons, very simple operations done seemingly randomly here. So you're randomly choosing some pairs and then you are computing this string. So this is now the signature of this patch. When you match it to another patch in another image, you will match these two strings. Of course, you need to check the same pairs. You can't again choose another random values of pairs. You have to choose the same pair tests. So the locations should be the same. And surprisingly, this works quite well. So the advantages of this is super compact. So the length is small, but also to compute them is fairly quick. It's simple intensity comparisons. And the other interesting thing is the distance between two such strings is just an XOR operation. So before, if we had two vectors of float points, to compute the difference between the two descriptors, you would have to compute some kind of a Euclidean error. So x1 minus x2, the whole square plus x plus, yeah. So the individual elements squared and then square root even or something like this. Whereas now, it's a simple XOR operation. If ones are at the same place, it's good. If they're flipped, they're bad. It's a simple XOR operation, which is also called as the Hamming distance between two strings. And you can do the fast comparison as well. So both computation and as well as the computation of the descriptor and computation of the distance between the descriptors, both are super fast. So based on this general idea of binary descriptors, there are a few different strategies. The main thing that differs is how do you choose those pairs. That's really the difference between all the binary descriptors that are out there. There's a few other tricks, but that's primarily the main difference. But one thing to remember is you must use the same pair. It's like a test, right? I'm testing the two pairs. I need to test at the same locations. I can't test at arbitrary locations. The test needs to be the same, and the order in which the test is done also needs to be the same. The pair order needs to be the same, right? So those are the two things you need to keep in mind. And so once you fix your sampling strategy, then you are done. You can use the descriptor and do the comparisons. The first such method which became very popular is called as brief descriptor. Has anybody used this descriptor in their projects? No, okay, so something new for you. So brief stands for binary, robust, independent, elementary features. Elementary features because it's just the difference between two intensity values. They're independent because each of the pairs are independent of each other, and it's binary because the output is only 1 or 0. So that's the brief descriptor. It was proposed around 2010, and in their implementation they use a 256-bit descriptor. Although the number of bits are more, SIFT uses a 128-bit descriptor, but they're storing float values. So actually float values take 4 bytes versus these are just 10 bits. It's literally 256 bits that you have there. And then in the original paper, they tested different things. They tested different ways of sampling those pairs. And it was quite interesting, the experiments. So the experiments had these 5 sampling strategies, right? So the first 3 almost looks like random pairs. So what's happening there is that a line corresponds to one start point and one end point. So each line corresponds to one pair for which a 1 or a 0 is computed, right? The first one is actually uniformly randomly sampled. You take the image, it's some maybe 100 cross 100 image. You uniformly randomly sample locations, and then you make the test amongst these uniformly randomly sampled pairs. The second one, can somebody guess what kind of a sampling? So given that the first is a uniform random sampling, can somebody guess what G2 sampling would be? What do you observe with G2? All of it looks a bit like modern art, but what's the middle one like? What's G2 like? Maybe you need to blur a little bit. If you blur a little bit, you'll see the answer. So a hint is it's somehow more crowded in the center and less crowded in the sides, right? So what kind of a distribution can give you that? Yeah, a Gaussian distribution. So it's centered around a mean, and then you will have fewer samples around the edges. So the second one is a Gaussian distribution. And then the third one is actually quite difficult to guess, but it's a mix of uniform random and Gaussian. What's happening is the first element of the pair you choose uniformly randomly wherever, and the second element you choose a Gaussian around that point where you sample the original sample. So it's first a uniform random sample followed by a Gaussian sample, and the property of that is therefore those lines are quite short. So compared to the pairs that you see in G1 or G2, G3 are often quite close to each other, and the reason is because you're looking everywhere, but the second sample you're doing is a Gaussian sample, so you're often looking quite close to the second sample. So these were the 3 samples, and the fourth one was done on some polar grid. So you break up your space into angles, and then you're doing around different radiuses and angles, so it's much more fixed, it's not random. And the final one is some kind of a spiraling out scenario. So they tried all these different sampling pairs, and I mentioned that the first one was uniform random, then Gaussian, then this mixed Gaussian, and so on. And when they analyzed the performance of the descriptor uniqueness, they found more or less the first four work fine. The first four work fine, but the one with the very fixed kind of the star pattern doesn't work really that well. So in the end, I think you can use any one of the first four methods, whatever is quick to do. And when you use brief operator, I think they let you choose this values. So this is brief. The one that's more popular in robotics is the ORB, or the oriented rotated briefs, oriented fast rotated briefs. Has any of you used the ORB features for their projects? If you're doing visual odometry, there's a very popular SLAM algorithm called as the ORB SLAM, which uses this one. So so the one thing that the brief descriptor didn't really care about is the rotation. Because if I take the patch and if I take two pairs, let's say number 3 and number 7, I compute the test and I get a 1 or a 0. But now, if in the new image that patch was rotated, then your 3 and 7 will be located at a different place. So the test will fail. So the brief descriptor is not rotation invariant. It will only work if you kind of see the objects from the same viewpoint. So to fix this, the ORB was introduced, where one of the things that they add is adding a rotation compensation to make sure that your binary descriptor can also work when your images are rotated with each other. And the second one is they actually learn the optimal sampling pair. So they took a big data set and then tried different samplings and found out that sampling strategy which was best. So previously it was more hand driven. We tried different commonly occurring probability distributions. In this, it's learned from data. So that's the two main differences that the ORB brought in. And in terms of rotation compensation, the main idea that they added is, for a patch, you need to find the main orientation of that patch, in a way similar to what SIFT does. But in this case, they do it using what are called as image moments. So image moments is a general concept with this formula where a moment of any given point is given by the x to the power of p and y to the power of q times that image value. But in practice, you're just using p and q as 1 to get the center of mass. So if you apply the moment formula, you can get the center of mass of that image patch. So in this image patch, there is this triangle, right? This triangle ka center of patch is somewhere here. That's where most of the center of mass is accumulated. And the distribution is accumulated in this direction. So the orientation is somehow towards this direction. And moments of the image capture these. So they use the moments of the information, moments of the image to compute a center of mass and a theta orientation. So theta can be expressed as a moment, as a tangent of the 0-1 moment and the 1-0 moment. So we won't go to the proof of it, but it's actually quite nice to see how these formulas come out. So if you do the moment 0-1 and moment 1-0 and take the atan of that, you'll actually get the major orientation of that area, of that patch that you have. So now that you know what the main orientation of the patch is, you can actually compensate for the new sample. So what's happening here is S is your original sampling pair. So let's say I took the sampling pair 3 and 7. My image was rotated. So I now need to re-rotate that image using this transformation matrix using the center of mass and theta that I computed. So essentially you're bringing the patch in image 2 in the same orientation as the image 1. Now you can match them again. So that's the trick that you're doing with the orb bit. Because of this, now you get rotation invariance as well. So now you can use binary images even when you have images that are at least to some extent rotated. This of course depends upon the fact that the theta and the c that you estimated are good enough. Sometimes what happens is the theta and the c that you estimate is not good, and then you're doing a bad patch transformation. It won't match, but that's part of the game in that sense. Right. So yeah, so in the ORB they use these learning sampling pairs, and there's some technical rules on how to choose these pairs, and they kind of make common sense as well. The pair should be uncorrelated. Let's say if I'm looking at two pairs, if I look at two other pairs which are roughly next to each other, I am not getting a lot of new information. So your pairs should be spread apart as much as possible, and that's the spread apart comes in the high variance part. So the samples should be chosen such that the strings that you generate should be as far away from each other as possible. So those are the two cost functions that was used to optimize the sampling strategy in the ORB features. And in the end, again, they also choose 256 pairs, do the test, and come up with a 1-0 string which you could use for matching. So just to do a quick summary, so in practice, ORB is about 100 times faster than SIFT. So like I said, for most kind of the images we will see in the example, SIFT takes about 1 second per image feature computation in image. So this is 100 times less. So that's 10 milliseconds instead of 10 milliseconds instead of 1 whole second. So which basically means you can process 100 images in the time that you would have processed just one with the SIFT. It's smaller, so the ORB is just 256 bit, whereas SIFT is 4096 bits when you convert the float values out to bits. The downside is ORB is not scale invariant. So we didn't do anything for scales. We fixed the rotation by taking care of the orientation bit, but we didn't do anything about the scale. So if you observe the same things in the environment from drastically different distances, this starts to fail. So that's the cost of not having the more expressive feature. There are some variants which have been proposed where you can get a little bit of scale invariance by using an image pyramid. Does anybody know what an image pyramid is? It's very commonly used in image processing. We actually also saw it when we were doing the difference of Gaussian's descriptor. So image pyramid is essentially you take the original image, you take half of it. So whatever you do on the original image, you also do on the image that's half the size and quarter the size and 1/8 the size. And the reason you do this is you catch different scales. It's a bit like you have your eyes, you squint a little, you squint a little bit more. When you squint more, your vision changes its focal length and objects appear at different resolutions. So it's the squinting equivalent of image processing that you can do. So if you want to just, if I kind of really focus, I see details of all of you, but if I squint a lot, then I see each one of you as a blob, so to say. And if I'm only interested at the blob level, I should use that level of the pyramid where the resolution is a bit lower. Right. So that's image pyramid, and that captures this, the scale part of it. And most modern SLAM systems you will see have ORB or some variants of ORB that's being used, primarily because it's super fast to use them and fairly robust. So the performance is not that worse than SIFT, right? So this summarizes the part about descriptors, and we'll go into the part about actually using these descriptors and key points to do place recognition systems. So if you are sleeping till now, the message to take home is key points will define the XY location, which are interesting. The descriptor will give you how the local area around that key point is. And there are a couple of ways of doing it. You can do a high quality one based on image gradient descriptions using SIFT, SURF, etc., and a binary version of it using brief and op. So that's kind of the takeaway message. So any questions at this point before I start the place recognition bit? Okay, I assume then you're understanding everything rather than not understanding anything, but okay. So the next bit is how do we do place recognition using the tools that we saw, right? So I come back to the image that I had shown before. The problem of place recognition is as the follows. So you have a database of images that you have from, let's say, your past experiences. So let's say you're building an autonomous driving car. In the first run, you don't let it autonomous, somebody drives the car, and then you record the images as you drive, right? Now, the next time the car wants to go there, It wants to find out where in the images that you recorded before are you currently located in. So that's the question that you're trying to answer here. And we want to put together some of the tools that we learned today in order to complete this, achieve this task. So formally speaking, the place recognition problem is that of finding images in a database which are similar to a given query image. So the current image is called a query image, and the database images are typically called as reference images. And the way we want to do this is by computing image similarity. That's what you also did, right? So you were trying to see how similar is this image to each one of the other images that you saw, or when you were given a pair, you were trying to come up with some kinds of similarities. If a computer has to do it, it has to come up with some way of doing this numerically. So what's a way of representing an image such that you can compare them numerically very efficiently is what we are looking at. So you want an algorithm that's able to do this, that's not very specific to saying, oh, there is a window there, there is a door there, because that's much more difficult to specify to a computer. So you need to come up with a more general approach to solve this. And here, the bag of words approach, which is the algorithm I'm going to explain, is actually borrowed from the text data mining community. So the original problem that was studied in document mining was, you have a whole bunch of documents. So you have a library full of books. You are interested in fetching a book about, let's say, computer vision. How do you know which book to go to, right? So the text mining community developed several of these algorithms, and we kind of adapted for the visual aspect of place recognition or image retrieval. So a very simple idea would be, you take every book, somebody has to take every book, and then make a word count for each book. How many times the word computer came in, how many times the word vision came in, how many times the word kernel came in, how many times the word dog came in. So let's say the English language has 10,000 words. You take each word and create a histogram of the number of times a word was occurring in that particular document. That's a signature of that document. And then when I say I want a book which is about vision, then maybe I just get back a book which has a high count for vision in it, for example, or something similar. So that's broadly the idea. And this is also used, I don't know if some of you are doing some literature review. This was a portal that we used to use in my previous lab, where if you have a particular paper, there was a button which you could click, which would give similar papers. And essentially the way this did this was exactly the same as what I mentioned. You create a signature of the terms that have occurred in those other papers, and you retrieve the closest ones. So in a way, this is what you also do when you're doing on maybe Google Scholar or some other place where you're retrieving. This is one of the classical ways of doing it. By the way, the problem that we are solving of image place recognition is the same problem that Google reverse image search does. You put in your image and you ask it to fetch from the internet the other images which look similar. So this is not just used for robotics, but also for, in general, database retrieval problems where you want to do image-based searches. Right? Okay, so this was for words, but how does that scale for images? So essentially, we treat an image as a combination of visual words. So if you look here, maybe the picture of the lady here, it consists of eyes, it consists of maybe part of the head, hair, and so on. So each segment that you see here is actually a visual word. It's the equivalent of what a word in English would be, but it's a patch of image which represents a particular word, and the count would be its signature. For example, if there is a word called as eye, she has 2 eyes, so the eye count would be 2. Maybe the ear count would, in this case, it looks like 0 because the hair is covering it. But in general, you come up with a representation that's a combination of words that you can easily see in the image that you have. Once you do that, you can throw away your image. You're now only dealing with this collection of visual words that represent that image. Right? So visual words are those features which can be identified in many places. So for example, let's say, this is actually from a painting, I think. Let's say if you were trying to identify what painting in a museum is the current picture from, you can take all the paintings, you can sample, we'll see how to build that sampling procedure. We can sample interesting features that come up. Let's say eyes, nose, jewelry and things like this might come up. And those are the things which we'll use to represent the image as. So in a way, now this image is turned into these small segments of features. And we will reason based on these smaller segment of features rather than the full image itself. So the first thing that you actually need to do is to create something that's called as a code book or a dictionary. It's similar to the Oxford English dictionary that you have, right? There's a bunch of words. Everything that I say in principle should come from a word from that dictionary, right? Similarly, all your images will be a combination of words or visual words from your code book. But we first need to create this code book, right? So for English language, we have this code book given to us. But for image features, this code book is not really given to us. So we need to create that code book by ourselves first, right? So that's the first process. And this process is also called as vocabulary generation, because vocabulary is the way you express a particular language. In this case, the visual language is expressed through the visual words that you have, and you need a vocabulary to do that. And then once you have a vocabulary, you can then represent each picture as a histogram over that vocabulary. So what is happening here? For example, we have this picture of the lady here. This, and on the x-axis we have the vocabulary. Let's say for now our vocabulary only has these 4 things: an eye, the bottom part of the violin, some part of the cycle, and some part of the face or something like this. So it's just an illustration. In this case, our vocabulary has only 4 words, and I need to express the image in terms of a count of those vocabularies. So for the human body face here, the count of human features should be high. Maybe the eye is high. For the bike one, the bike parts will be high. For the violin one, things that look like violin will be high. So now you have converted this image to this histogram, right? Somehow similar to what feature descriptors were doing, but there's a difference. So the local feature descriptors that we computed before only looked at a small patch around your key point. Whereas now what we are trying to do is we are trying to describe the whole image as a combination of something that's consisted of smaller visual words. So this histogram describes the entire picture, not just the eyes or not just the nose or something like this. What we were trying to do before is to describe a very small area in the image. Now we are using those tools. We'll use those tools to describe the whole image as a collection of those smaller features that we have. And then once we have those histograms, then the place recognition task gets converted to an image histogram matching task. So you have to now match one histogram with the histograms of all other pictures in the reference trajectory or the database, and retrieve the closest histogram that you have here, right? So we can see this in a more realistic example here, or again an illustrated example actually. So this is taken from a data set for self-driving cars, where this is a camera mounted on a car going through many streets. So first you have the image, you need to convert it into histograms. How do you do it? You have your input image. First you convert it into grayscale and then compute the SIFT features. So these are the green bits that you see are the SIFT features. You see features of different scales as well. For example, this whole shrub area is covered in this big feature, but there are also very small features which are capturing the fine details like the corners of the windows and so on. So the first approximation, so to say, is image to SIFT features. The next approximation is these SIFT features are also too many. So for that image, maybe we get about 1,000 SIFT features, but I want a much more compact representation for that image. So I map those SIFT features to a dictionary of words that I've computed. In this illustration, my dictionary has, for example, 3 words. One is a green colored word, one is a blue colored word, and one is a pink or magenta colored word. Now I map those SIFT descriptors to one of these words. So these two things kind of look the same, so they both get mapped to the same visual word, something that says building, for example. and these three paths map to the same word, let's say shrubs or trees, and this word gets mapped to something like a street or whatever other man-made object that's there. So you are once again compressing your information from SIFT features to smaller visual words. So we went from images to SIFT features to words. So we came down in terms of the number of elements you need to express this. And actually after this, you can throw away the image. So as far as we are concerned, our image is only a collection of these words, whatever, 1, 2, 3, 4, 5 blue words, 2 magenta words, and 1 green word. And actually this is also more than what we store. We actually don't even store the locations. We put them in a bag, which means we lost locations. All we know is 5 of blue, 2 of magenta, and 1 of green. We've even lost the, or we can put it, but in the most simplest approach, you even lose the locations of it. So your image now is a simple histogram of these numbers. And this makes it very computationally effective to then compute. So in the end, we have gone from our image to a histogram representation of that image. This is the first step that you do before doing your retrieval, right? And this histogram will basically say, I have 5 of blue, 2 of magenta, 1 of green, and 0 of yellow and 0 of red. Let's say there were, in your dictionary, there was also yellow and red words, but in the current image, they don't occur at all. So the histogram will only show 0 for those ones. So this is your signature of the current image that you have. Now the question you might ask is, where did we get these words from? So where did I get the blue word from? Where did I get the magenta word from? We don't have a Oxford dictionary for image patches, right? So we need to create that dictionary of image patches. So that's the next question that we look at. Essentially, if you think of a dictionary, it's those things that sit on the x-axis on our histogram. These are the words that we want to compute. And that's the question. The question then is, how can we compute these words such that they are unique? Because we don't want many words which represent the same thing. We want words which are kind of spread apart in the visual space that is there. So another point to note is, once you create a dictionary, it should remain fixed. So we can't arbitrarily make up new words. Now, if I ask you a question and if you answer in a answer using words that are not there as a part of a dictionary, I cannot understand you. It's the same with the image retrieval part. You need to fix a bunch of words, right? So how can we actually compute these words? The way you do this is through data, through unsupervised learning. So what you do is you collect a whole bunch of data from your sensor. In this case, since this was mounted on a car, it was a camera mounted on a car. These are just trajectories of the car driving through different streets over different seasons even. So this was, I think, in the summer, this was in the winter, and you collect all the different variations you can collect. So you need to make it as wide as possible, while of course restricting the total number, of course. And then what you do once you have that data set, so in this case, for example, let's say we have 10,000 images that our car has explored over. You then convert those images into descriptor vectors of local features. So this is using SIFT. So you take each one of these images, compute SIFT features. SIFT will give you 128 float values. So you have that 128 float values here. For example, image 1 has 100 such features. You put them in a column here. Image 2 has another, let's say 200. You put them in a column here, and so on and so forth. So you keep concatenating all the SIFT features that you have ever seen in your training data set, for example. That's a large number of SIFT data sets. We don't want that many words, right? So for example, we have 10,000 images. Each image has, let's say, 100 features. So that's 10 to the power of 3 times 10 to the power of 2. That's 10 to the power of 5 words that you'll end up with, right? But that's a lot of words to express similar things. Let's say we want to express things like buildings, roads, that are way too many words. So we want to compress this. Okay, maybe before I show the answer, what's an unsupervised way to compress large number of vectors into a fewer set? PCA is one way to do it, yes? There was another answer? Yeah? Yeah, PCA I don't know if people have tried PCA on it, but the thing that they have tried, I think the difficulty is because these matrices become very big and taking the eigenvalue decomposition of it gets tricky, I believe. So that's why I think PCA is not as used. The method that's commonly used is k-means clustering. So you have n vectors, you want to bring it down to k, n is let's say 1,000,000, k is 100. So you want to bring down those million vectors into a 100 vectors kind of a thing. And the way you do this is you say in the high dimensional space, whatever SIFT vector is 128 dimensions. In a 128 dimensional space, which is of course here shown in a 3-dimensional bit, some of the features will fall close to each other. So maybe all the visual features which are on the road will fall close to each other on the 128 dimensional plane that you see. And therefore, if you kind of create an average of those, that will be like the average road vector. Maybe this is the average bush vector, this is the average building vector, and so on. So you can take all these features which look similar in the higher dimensions and average them out to say this is the average look of that place. So you can end up saying all these belongs to the red word, all these belong to the green word, all these belong to the cyan word or something like this, right? So you can cluster, and this way you can bring down your dimensionality of your words. So once we have the features, you do the clustering, and we do this using something called as a k-means clustering. Essentially, you want to partition your data into k clusters. Usually you give the k. This is something that's usually something done manually tuned based on your database challenge. Each cluster will be represented by a centroid, which is the center of mass of that particular cluster. And the goal will be to find k clusters such that we can assign for any new SIFT feature, we can assign it a particular cluster. So the informal way the algorithm would look like is you arbitrarily choose k. Let's say k is 2000. So we have 2000 words that we want to build. We want to build a dictionary of 2000 words. We just start randomly, and then we repeat the following process. So for each data point, so each SIFT feature that you computed, compute the distance to these 2000 clusters. And whichever is the closest one, assign that ID of that cluster to that particular descriptor. So this way you will assign colors to each one of your data points, and then you recompute the centroids. Once you have assigned the group belonging, then you redo the class assignment. A bit more computer science way of writing this is in a pseudocode. Here you say you initialize each of your examples. So you have k means, k centroids. You pick a random sample, compute the distance of that sample to every one of your means. The mean which is the closest, or the minimum mean, will be assigned to that particular descriptor. So this is the math way of saying the same, and then you compute the centroid of the point corresponding to the cluster. So this is a little bit more easy if you just look at the image. So let's say we start with the data on the top left, where in the beginning we don't have any clusters yet detected. So all the data points belong to some unknown cluster. I arbitrarily take 2 points in the space, in this case, the blue cross and the red cross. Then for each data point, I compute the distance to both the means. So I take a data point, for example, here. I compute the distance to this one, and whichever is the closest, I assign that color. So maybe that was an ambiguous example. Maybe if I take a point here, the distance to the red one is closer than the distance to blue one, so I assign it the red color. And I keep doing this for every single point in the data set. And then I end up with this result. Right? So I end up with the result where the right diagonal part of the image becomes to cluster red and the blue becomes to the cluster blue. Then I recompute the means. So I change the position of the x cross here to be the centroid of the red points only. So you see that moves the red cross to somewhere here, right? Then I redo this assignment. So all these blue points will get red, all these red points will get the blue assignment because they're closer to the blue mean. And then when I redo it, I get a much better separation. So when I do this for a few steps, I will converge and no more changes will occur. And at that point, I have found two clusters where all these data points belong to this blue cluster, all these data points belong to this red cluster. And this is what you also want to do with your visual features. So when a new SIFT feature comes, you will attach it to the closest cluster that you have found. That's the assignment to the visual word that you have. So yeah, k-means is the standard way of doing this. It is sensitive to outliers, so you have to do some kind of outlier rejection, but broadly it works. It works out of the box if you have fairly well distinguished features that you have. So okay, so how does it look for our visual place recognition task? We took our images. So this is for building the vocabulary still. We take our training set. We compute the features. Those features, let's say, ended up at different parts of the space. So these features could have come from any image, by the way. So for example, there's road here, there's also road here. So the road feature from this image, whatever, image 5 might end up here, and the road feature from image 1 would also end up here. That's the thing that we are clustering. We are finding all the road features to be together and all the building features to be together. So if you do k-means algorithm on the features, you end up with these visual words which are represented in these different colors that you have. Like I said before, all the images are then reduced to these image visual words. So let's say these are all the visual words corresponding to those images, and visual words are reduced to the histogram. So in the end, every image gets turned into histogram using the vocabulary that you have just built, using the dictionary that you have just built. So some notes to remember here is one of the things that we have given up is spatial arrangement. Because we are just converting all of the things into counts, we have given up on spatial arrangement, which was an interesting, important cue that we were using as humans. We saw that on the top of the building there is a chimney, and therefore you should look for a chimney on the top of another building. Those kind of things are lost here. Spatial resolution is lost. It's just the count of things, right? So that's one of the downsides of using a bag of words model that you have. The other thing that people often struggle with is to find a good vocabulary. So if the vocabulary is too small, then many different things gets clubbed into the same things. If the vocabulary is too large, every image will map to slightly different words. So for example, if you have seen roads in sun and if you also roads when it was cloudy, ideally you want them to map to the same word. But if my vocabulary was too large, maybe I have a sunny road and a cloudy road image patch, and I would not be able to match those two words. So the word number is something that's actually a bit sensitive to performance that you have. Right? So once we have the vocabulary built, how do we actually find the tasks, which is finally solving the place recognition task? Your input will be the database of images and a dictionary and a query image. So that's what you will give in, and the output will be n most similar images in the database that match your query. So this is the formal way in which a place recognition task is formulated. So now it all comes back to the following question. So since we have converted all of our images into histograms, then the question is, how do I know if these two histograms are close to each other or these two histograms are close to each other? What's a way of measuring similarity between histograms? Any guesses here? So what would be the ways to measure distances between two histograms? So we did something similar before also with local features, right? Local features were also some kind of histograms, right? So here we have two histograms. What is a way to compute a distance between these two histograms? Yeah. So one of the simplest ways is just the Euclidean distance or the mean squared error between these, right? In the end, there is a string of numbers. You're looking for the difference of those numbers. So when you do mean square errors, you might want to do some kind of normalization before, because maybe some images have a lot more features than some other images. So you might want to divide by the total number of features or things like this. So some kind of normalization is needed there. Yes, mean square error is one thing, and in literature, there's 2 or 3 different ways to do this. Euclidean distance, like you mentioned, is one of the common ways to do it. The other way to do it is actually looking at what is called as the angle between vectors. If you have vectors that are normalized to 1, you can actually think them as directions in the environment. Rather than as lengths, you can think of them as directions. Then if you compute the angle between those directions, that's also a measure of similarity. So if your vectors are similar, they will align in similar orientations in the space. Whereas if the vectors are very different, they'll be orthogonal, for example, to each other. So you can look at the angle between the two vectors as well. And in many place recognition literature, actually angles tends to be the most stable way to do this rather than the distances itself. And the third way to do actually is what's called as the Kullback-Leibler divergence. So has anybody heard of Kullback-Leibler divergence before? KL divergence. You must have. So I'm sure all of you took many machine learning courses, and you would have been exposed to the word, at least, the Kullback-Leibler divergence. No? Okay, so maybe the opposite question or the other corollary question would be, if I give you 2 probability distributions, 2 Gaussian distributions, for example, how will you tell me that these 2 distributions are close to each other? What's the metric that you will compute? Yeah, for Gaussian, maybe you can look at the mean and the variance and you say, okay, the mean and the variance are close to each other. Let's say now I have a more weird shaped distribution. So let's say I have a distribution which maybe looks like this, and I want to see how close is it to another distribution. Maybe it looks like this. So how do you compute distance between these 2 distributions? Are they close? How close are they to each other? Yeah, so that's one way to do this, and that's called as the optimal transport method. So how do you twist this initial distribution to map it to the other distribution? There are a few ways of doing this. So it's like molding. How much do I have to change distribution 1 to match it to distribution 2? That's the other way. And the third way is actually the Kullback-Leibler divergence. That's a formula which takes a logarithm of the 2 ratio of the logarithm of the two probability distributions and comes up with a square. So whenever you have 2 distributions and you want to compare how 2 distributions are, typically the first thing you would do is a KL divergence metric. Like you said, if you have 2 vectors, the first thing you do is a Euclidean distance. When you have 2 probability distributions, the first thing you typically try is a Kullback-Leibler divergence that you do. So I said that the angle similarity is actually the thing that often gets used. So here are the formulas for those similarity distances. So similarity and distance is, let's say, 1 minus the other of each other. So similarity is how close they are to each other. In this case, this is just in a way, the dot product, right? So the dot product of one vector on the other vector normalized by their lengths is cosine theta. That is literally the definition of the dot product. Whereas the cosine distance is nothing but 1 minus that, because the cosine similarity will always be between 0 and 1. And if you argue in terms of distances, it's 1 minus that. If you argue in terms of similarity, it's just the cosine distances, right? So now we have a way to measure similarity or distances between 2 words. We know how to convert your images to histograms, and now we know how to compute the distance between 2 histograms. So these are the tools we need in order to actually do the place recognition. So I'll do a quick programming demo of this to show how the results might look like. Okay, let it reconnect. I'll probably just go through the code in this. So we'll share this with you after the session, so you can go and play this. Yeah, in this case, we take a popular data set that's used for place recognition called as a New College data set. So you'll see how it looks like. Oops, I think. Okay, so yeah, one thing I didn't plan for is that it takes a bit of time to run this. So I'll just run these and then explain the code so that we don't wait here for 5 minutes, just waiting for it to finish. So how many of you are familiar with using Colab for doing Python notebooks? Yeah, okay, a lot of you are familiar, so good. So you can play with it afterwards. So in this case, first step I did is just download a data set. I will use this data set both to learn a vocabulary and then use that vocabulary to describe an image and use that histogram representation to retrieve a similar image, right? So that's the problem we set out to solve. Okay, so some file. So this particular data set has 2,146 images. So the reference database has 2146 images there. Then I'm computing the SIFT feature for each one of those images. And as you see, it takes some time. So it's roughly 1 second per image. So it has to compute the SIFT images for all the 2,146 images that it's doing. So yeah, while it does, I'll explain the rest of the code. Maybe I should have used ORB here and have been a bit faster. Next, what we do is, okay, here I just wanted to display some features. I'll display it after it's done. Yeah, cannot show you before. So the one thing that I said, when we had all these images, we were computing. We had a whole bunch of training images, right? So we have in this case 2,146 training images. And so on. So what's happening is for each one of these image, I'm computing SIFT features, right? So maybe these are 100 of them. Similarly, image 1, image 2, I compute SIFT, maybe another 100 of them and so on. And we said there are 2,146 of these. So when I ran this last time, in all, we ended up with 5,500,281 some. So about 5 million SIFT points in the entire training data set. So those are definitely too many for being words, right? And this has, the other dimension as 128. Can somebody say why the other dimension is 128? So this is the entire descriptors all stacked together. So there's 5 million cross 128. So 5 million is 5 million individual key points that you figured out. And 128, what is this 128? It's the size of the descriptor. So each SIFT is 128 bit long, 128 numbers. So that's the size. Right. So okay, it's still computing the features. Let it compute. Then we come up to the generating a vocabulary part. Right. So what is the first thing you need to choose when you want to generate a vocabulary? Yeah, the K, the number of words, right? So how many words do you want to do? So in this case, we set K is 2,000. So of the 5 million vectors that we have, we want to compress it to 2,000 vectors in all. And here I just use sklearn library to do this. How many of you have used the sklearn library to do something? Okay, quite a few of you. So good. So that's the standard machine learning library in Python. If you're not confident of your own programming skills, which I'm not, you go and use the sklearn library. It works well. And then it will basically project your 5 million vectors to one of those 2,000 vectors that you have, right? So you'll create the dictionary using the k-means algorithm. Okay, so just now it took 4 minutes for the SIFT algorithm to process 2,000 pictures. And just to show you, the SIFT features look like this. So it's the same picture shown twice. So on your left is the original image, and on the right are all the features at different scales that have been computed, right? So you have some features which are big, where you have like blob-like structures, and some features which are small, which are more high frequency things. So this is just the first image. we did this computation for 2146 images, right? What did I do? Something broke here. Oops, I have to run this. Okay. The k-means fitting will also take some time. So this will now find the 2000 clusters from your 500,000 data points that you have. So we let it do its thing. So in this particular case, it's a very smart implementation of this k-means approach called as mini batch k-means. So if you remember the algorithm that I explained, when I was doing an assignment, I said take each sample and compute the distance to all the means. So in this case, the number of means are 2000, which is fine, which is not too big. But I have 5 million samples. So I need a for loop over 5 million samples to compute the distance to 2000 centers. So that's 5 million times 2000 computations that you need to do just for one step. So that's very computationally intensive. So what this mini batch k-means does is it's a stochastic version of k-means where you randomly sample a batch of, let's say, 10,000 points. So instead of working with 5 million points, you only work with 10,000 points, and then you try to find within those 10,000 points what's the best mean. And what people have found is if you randomly sample in every iteration, it more or less converges to the same solution as if you had used the entire data set. There's another very popular algorithm in which you do this, and which I'm sure all of you have used. Which one is it? Where you make a small batch while doing an update? Yes, exactly. So the stochastic gradient descent also does the same. In principle, you should take the gradient of every sample point while making the movement, but you do it with a batch size of even 5 or 10, and it tends to work. So this k-means is, let's say, your stochastic gradient descent equivalent of the k-means method that you have. So okay, it's doing something. I think it stops about 1300 or something like this, if I remember correctly. So once you have the words, what will you do next? Sorry? I think you were correct. So what were you saying? Yes. So once you have the words, convert your images into histograms, right? I'm still waiting for the vocabulary to be built. So the way you usually do this is you only build your vocabulary once. You don't have to do it every time. So you collect very varied images, you collect them, you compute the means, you create your dictionary. It's like we're not creating a new English dictionary every year. We just have one dictionary and you keep using it. That's the idea. You do it once. Of course, if you go to a completely different data set, for example, all our training data sets were from images taken on a car in a street. But then if you now want to do place recognition inside a classroom, it won't work well because the words required to express a classroom are different from the words required to express the scene on a road. So you might need vocabulary for outdoor environments, vocabulary for indoor environments, vocabulary for agricultural fields. These are all different. So at some point it converged. And actually, if you look at the final thing, initially it thought it needed 55,000 iterations to compute this solution. But after 1378 iterations, it actually stopped. It stopped because it says it converged, and it says a lack of improvement in inertia, which essentially means a lack of any change. So you had some k-means at the 1377 step, and the same answer repeated at 1378 or a few times over. Then you say, whatever I'm doing, the answer is not changing, I can stop now. So you can stop before the number of iterations that you actually planned for. Okay, now that the words are ready, now I want to compute the histogram representation for each of the image. So here that's what I'm doing. So I go through each of the image. So for each descriptor in the image, I use the k-means to give me the nearest words, and I use that words to stack them into a histogram, right? So how many histograms will I have? So my data set has 2146 images. So you need 2146 histograms as well, right? So because we're only working with histograms. This is fairly quick. If you see here, mapping from, once a vocabulary is ready, mapping from features to histograms is fairly quick. So we are taking probably less than a minute to process 2000 images in this case. Right? So this is done. So now we are ready. So now we are ready with the raw material for our image retrieval task. The image retrieval task is now given a query image, find the nearest image in the data set. So in this particular data set, actually this was taken using a handheld, so this uses the Oxford New College data set. It was a camera, which a person was going around in a campus, like here, like the IIT campus, they were going around. And what they also did is they went around to the same places multiple times. So I went out the road, I came back here, and I went out and again. And my task is, when I came back, I want to recognize that it's the same place that I was before. That's the task that I'm trying to solve. Right? So in this case, I set the query index as 1000. So I'm saying, give me the image that's closest to the 1000th image that I saw. So let's say if I pick up the 1000th image, it has some histogram, because technically now we don't have any images. All we have are histograms. This is how the 1000th histogram looks like. There are a few more numbers there. Then I match it against all the histograms of other images using the cosine similarity. So I use the cosine similarity. I compute distances between my query image, the 1000th image, with all the 2146 images that I have. There are more smarter ways to solve this, but the simplest way is just match against every one of those images. And I print the index of the top 10 here. Of course, the first index that it returned is itself. The image is closest to itself, right? But that's not the interesting bit that we want. We want to find an image other than itself, other than the same image, which are the other ones. And it says image number 602, 998, 1002, and so on are similar. I mean, it may be, unless we plot, we'll not know. So let's do that. Let's do that plot. I think I have to run this one. Then I have to run this one. And so, okay. So what you see here is the query image is actually the image here. The first image is the query image. That's the input image that I gave. And then it found the closest image, which kind of looks the same. It looks like it was taken from a very close place. And to be honest, most of the 10 images that it retrieved look reasonable. They don't look completely wrong, right? So this is a way you can do place recognition. Let's check for a few other examples. So give me some ID between 0 and 2145. Who wants to volunteer? Any number? 708. 700. Okay, ठीक है. Let's see if it works for 700. So 700 का कोई histogram आ गया. So this is the histogram for that 700. Then we compute the distances, and then we plot the result. So yeah, 700 look like this. It's some wall of some building with some window. It returned this as the best estimate. I think it's the same window. So it does look similar. This one looks like a bit away, and actually we can see it from the index number. 700 and 702 must have been taken one after each other. So maybe that's also not as interesting. You can also keep a filter. Say, don't return me anything within an index of, I don't know, 10 or something like this, right? In that case, I will reject 702, 708, 698, 704. I will reject all of them. I'll look at 736. 736 is 1, 2, 3, 4, 5, sixth image. So if I look at sixth image, actually it's not correct. So the sixth image, although the visual words look the same, the sixth image may not be from the same place. But yeah, from as far as the bag of words is concerned, it thinks it has very similar textures. The same with the seventh image. If you show me, or if you yourself look at the first image and the seventh image, it could have been from the same place, right? If you move, so I'm talking about the first one there and the seventh one here. It has these brick structures which might be from the same building, just slightly further down, right? And then it returns something that's definitely something different. So there are limitations to these methods, but at least the top few that you got are actually quite good one. I think number 1000 is one where we have some good loop closures after a long time or something like this. Because not all places have been visited multiple times, returns will be just the close by images. So only some of the places have been returned multiple times. Oh yeah, this was the one that I showed before. Okay. So anyway, so we'll share the notebook with you. A nice experiment would be actually you take your mobile phones, go around the campus since you're anyway staying in the campus, make your own vocabulary, and then ask one of your friends to take a photo from their phone of one of the places that you visited and try to see if you're able to retrieve your image. Right? So this could be something that you do as an exercise. So you don't have to look at the Oxford pictures, you can look at IIT Bombay pictures. You go take your own data set. You can also do it indoors. So for example, a very difficult task is most of the classrooms look similar. So all the benches are there in the classroom, there's similar blackboards and so on. So if you really want to test, you can take also indoor pictures and then try to see if you're able to retrieve spaces. So there's one thing that I didn't do here, and maybe I'll give it as a homework to you. So currently I said you just compute the words and then match those words with each other. This assumes that all the words are equally important, right? If you take the corollary in, let's say, in a document, every book will have a lot of these, ands, all the connector words, there'll be a lot of them. So if you match these connector words that doesn't tell you something particularly useful about the book itself. So you want to give more importance to some words than other words. And there is a technique called as TF-IDF, term frequency, inverse document frequency. So look up for TF-IDF and try to implement TF-IDF, because what TF-IDF says is that I will look at term frequency, the number of times the word repeated, but I'll also look up how often it happens. If the word the occurs 10,000 times in your books, but it also occurs in all the 1,000 books that you see, the weight should be low. It's a very commonly occurring word which doesn't have distinguishing capability. So you multiply TF with the IDF score, which is an inverse document frequency score, which means the fewer number of books it occurs in, the more value it gets. For example, a word like Sobel operator is a very specific word. So you should give high importance to a word like Sobel operator, because that gives you much more information than a word like and, for example. The same happens with visual words as well. Some words, for example, most of the data here, okay, in this one, okay, most of the data here might have like some road that looks very, very similar, right? So all of them has the ground which looks very similar. So by matching a lot of features of the ground, you're not gaining much. So you should give fewer importance to the words which are on the ground. The other thing you would observe is a lot of these pictures have sky in them. So sky is there in all the outdoor images. So you don't really gain much from them. So you need to come up with the weighting which will give more importance to kind of unique distinguishing features than the other ones. So that maybe you can add, it's probably 3 or 4 lines of addition. You can modify this collab and then try that out as well. So when you go to more difficult problems like classroom identification, you might need the TF-IDF to solve it. So yeah, so that's all from the content side. I guess it ran an hour more than I had planned for, but since you're here, yeah, thank you for your attention, and I'm happy to answer any questions if you have.